Hello again, everyone. Welcome to our discussion of section 8.1, where we will be talking about sequences and series. Before we begin, please let me remind you to have a look at the section 8.1, skim through the section, spend about 45 minutes doing that, to get a feel for this subject and see some solved examples in the book. Then watch this video from beginning to end, and then second time take notes, read the book, and attend class and take notes of any important things that you might hear or see, or make a note of all the questions that you might have. Then go over the problems that are solved in the book and make sure you solve those problems without looking at the solutions given in the book. And please do the same thing with the problems I go over in this video. In fact, it's preferable that as we go through this video, even if you have not read the book yet, please pause the video whenever I get to an exercise and solve the exercise on your own paper before seeing my solution. Then, of course, please complete the homework for this section by the due date, and of course, review all the previous material to keep things fresh in your mind. Okay, so sequences and series, those of you who will be taking Calculus 2, you will see this stuff again and again, and any mathematics course that you have to take beginning with Calculus 2 and beyond is heavily relies on a discussion of sequences and series. You will look at this discussion in more detail in any class that is Calculus 2 or beyond. But what are sequences and series? Well, sequences and series, sequences are any list of numbers that has a pattern. Okay, if you can find a list of numbers with some kind of a pattern in it, you have a sequence. This means any list of numbers that are a random bunch of numbers is not considered a sequence. The numbers must have some kind of a pattern connecting them to each other and to the position within the sequence where they appear. What do I mean by that? Well, with sequences, not only there is a relationship between the numbers that are listed. So for example, this one, any number is the previous number plus 1, right? So that's a pattern. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4, and so on. So there is a pattern here. But not only we look for, in a sequence, we look for such patterns between the numbers that are listed, but also a pattern between the number and the position where it appears. So the number 1 is in position 1 along this list. Number 2 is in position 2. Number 3 is in position 3. Number 4 is in position 4, and so on. Okay? So there is a connection between these numbers that are listed, as well as there is a connection between these numbers and the position where they are located within the sequence. We can have sequences that are finite or infinite. So this ... that you see means that this sequence is an infinite sequence. It has no end. But this one, it has some terms, but it's a finite sequence because at the end there is an n. So this sequence has an end, and therefore it's a finite sequence. Okay, that's again an infinite sequence, again an infinite sequence, right? And again, of course, you can see the patterns here. You add 6 to any previous number to get the next number. So 6 plus 1, 7. 6 plus 7, 13. 6 plus 13, 19. So there is a pattern between the numbers and so on. And that one has a different pattern, right? So that one, you simply multiply the previous number by 2 to get the next number. 2 times 2, 4. 4 times 2, 8. 8 times 2, 16. 16 times 2, 32. So there is, again, a pattern there. So these are all examples of sequence. Now, within each sequence, oh, by the way, so let me talk about series here. Series is the sum of the terms in a sequence okay, so the sequence is any list of numbers that has a pattern, and the series is the sum of the terms in a sequence. Of course, we can have partial sums. In other words, we can partially add a certain number of terms or values in a sequence. It doesn't have to be all the terms. When we say series, we don't have to add all the terms in a sequence. Oftentimes we do that, but not always. We can, it's our choice. We can partially sum a sequence. So in that case, it'll be a partial series or a partial sum. Okay? All right. So a sequence can be given using the formula for its nth term. This is such important. The nth term formula, it's exactly what it is here, using the formula for the nth term. So the sequence, any of these sequences that, for example, we have up here, they can have an nth term formula for them. Well, what is the use of that? Well, if you have an infinite sequence that never ends, and you're interested to know what is the 2005th term in that sequence, right? What is the 2005th term in the sequence? If you're interested in knowing that, for whatever reason, you don't have to list all the terms all the way to the 2005th term to find out what that value is. You can simply use the nth term formula to find what is the value in the sequence that appears in the 2005th position in the sequence. You can use the nth term formula. The other use of nth term formulas is that you can program them into the computer, and that way you can make extensive calculations if that's what you're doing requires. Okay? So there are many, many, many different kinds of sequences in mathematics. So there are whole studies being done on just one or two of these kinds of sequences and series. So here are examples of some of the nth term formulas. So an refers to the nth term. So let me write that here. Let me define. an is the nth term. So if you're looking for the 100th term, that would be A100. And you would find it that way. If you're looking for the 5th term, that would be A5. If you're looking for the 20th term, that would be A20. Okay, so that's just a label. That's just a name. And generally speaking, you can leave it as n. So nth term means any term, but you can choose what n should be. If you're looking for the 500th term, n would be 500. Okay, so again, these are some examples of nth term formulas. So then, the other, let's look at some of these examples then. This one says use the nth term of a sequence, which we are already given. what they're referring to, this, use the nth term of a sequence, we are already given that. That's the nth term of the sequence. We have it. That has been provided that in each case below, and find the first two terms and also A10 and A15. So we need to find the first two terms, A1 and A2, and also find A10 and A15. Okay, so let's find that. If you feel comfortable with this discussion so far, and if you've read the book, you've skimmed through the book, I mean, you should be able to answer these on your own. So if that's the case, please pause the video and write down your own solution before you see what I have here. Okay, I'm assuming you've done that, and now you're back. So the first two terms would be A1, first of all. Let's plug for n. Wherever you see n, plug in 1 for it. 1 minus 1, 1 minus 2, 1 minus 3. And of course, that first one is 0, so it'll make the whole thing 0, right? So that'll be 0. So that is A1. A1 is equal to 0. That's the first term in the sequence. A1 meaning the first term. The second term, it would be A2. So let's plug in for n with 2. 2 minus 1 times 2 minus 2 times 2 minus 3. Okay, 2 minus 1 is 1. 2 minus 2 again is 0. 2 minus 3 is minus 1. Again, because of this middle term, the second term is also 0. Okay, so this is the first term of the sequence. This is the second term in the sequence. Okay, but then they also ask us to find A10 and A15. So A10 would be wherever you see n, plug in 10 for it. 10 minus 1 times 10 minus 2 times 10 minus 3. Right? Okay, what do we have then? We have 10 minus 1 is 9, 10 minus 2 is 8, 10 minus 3 is 7. Right? So that's 72 times 7. Let's multiply them together using my calculator here. So we have 9 times 8 times 7, right? 504. So that's the 10th term in the sequence. Do you see now why we need these nth term of a sequence? We can then find any term within the sequence very quickly. That way we don't have to list each value in the sequence. So this is the 10th term, right? And of course the 15th term, which is A15. So let's plug in 15 minus 1 times 15 minus 2 times 15 minus 3. So we have 14, right, times 13 times 12. I definitely need my calculator on this one. Okay, so 14 times 13 times 12. 2,184. So this is the 15th value within the sequence. Within that list of numbers, that's the 15th number in that list or sequence. So that's the 15th term. Okay. Is that clear so far? So we're using the nth term of the sequence to find any of those values within the sequence. We can do that here, but here we have to be careful because they're defining n as any value equal to 3 or larger. Right? Any value equal to 3 or larger. So don't start n with 1 here. N starts at 3. So this is a very important condition here. Okay, so let's do that. So the first term here will start at n equals 3. So a3 equals 3 squared minus 1. So that'll be 9 minus 1, or 8. That's a3, or the first term. That's the first term. And then a4 would be the second term. So 4 squared minus 1, it will be 16 minus 1, which is 15. So if you were to list this sequence, this is the nth term formula, but if you were to list this sequence, it would be like this: 18, comma 15, and then dot, 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 right? That's how you would list it. The first term would be 8, okay, because n starts at 3, does not start at 1 or 0. Okay, then they ask us to find a10 and a15. So a10 would mean to substitute for n with 10. So minus 1, this would be 100 minus 1, or 99, right? That's the 10th term. That's the first term. Second term. Okay, so I'm writing the position where these numbers appear in a sequence. That's very important. Like I said at the beginning of this discussion, with sequence, not only the connection between individual numbers is important, but also in which position in the sequence they appear is important. Okay, there are two things we have to keep an eye on. One, what is the value that is shown in the sequence? What relationship is there between those numbers that are showing in the sequence? And also, what relationship is there between each number and the position it appears? Is it in the first position? Is it in the second, the third, the fourth, and so on? And also, they ask us to find the 15th term. So, or A15 basically, that's what they want. That's what they want, A10 and A15. Okay, so A15 here, not the 15th number, but, so let me actually, I just noticed something. So this is A10. This is A10, but not the 10th term. Okay, because n starts at 3. So this may be the 7th term. Okay, but it's A10. And then 15 squared minus 1. What is 15 squared? It is, let's see. So 15 squared, it is 225. So 225 minus 1, it is 224. So this is, let's just call this A15. A15. Okay. All right. There are more examples on the next page. We have to do the same thing. We have to find the first two terms and then A10 and A15. Okay. So now you know how these work. So please pause the video, answer both of these, C and D, on your own paper, and then come back to the video. Hopefully our answers agree. All right, I'm assuming you've done that, and now you're back. So A1 is equal to minus 1/2 to 1 minus 1 power. Wherever you see n, substitute 1 for it. Right? We're substituting, n is the position of where this term appearing. It's the first position, so 1 minus 1. And any number to 0 power is equal to 1. Okay? So that's A1, the first term. Then A2 would be minus 1/2 to 2 minus 1 power. That would be minus 1/2 to first power, or power 1, and that's minus 1/2, right? That's A2. And then also they want us to find A10, so that'll be minus 1/2 to 10 minus 1 power, or 9, right? Minus 1/2 to 9th power. 9 is an odd number, so that means this negative is preserved, and then 2 to the 9th power, what is that value? So let's calculate that. 2 to the 9th power. So 2 to 9th power, 512. So minus 1 over 512. Okay, like that. And then, of course, A15. Or 14th power. So 14 is even, so it'll cancel this negative. So we have positive 1 over 2 to the 14th power. And that's going to be a large number. So let's see. So 16,384. Right? So positive 1 over 16,384. Okay. Do these answers match yours? If they do, wonderful. Okay, so you're coming along nicely. If not, and if you have questions, please let me know. All right, so next one, and I'm assuming you've already answered this question. So A1 would be minus 1 to 1 minus 1 power times 3 times 1 minus 5. So what do we have? We have negative 1 to 0 power times 3 times 1 minus 5, that's minus 2. Right? Anything to 0 power is 1 times negative 2 is negative 2. So that's A1, the first term in the sequence. Let's find A2, or the second term in the sequence. That would be negative 1 to 2 minus 1 power times 3 times 2 minus 5 equals. So we have minus 1 to 2 minus 1 is power 1 times 3 times 2 is 6 minus 5 is 1, positive 1, right? So we have negative 1, like that. Okay. So then we have to calculate A10 and A15. So that'll be 10 minus 1, right, times 3 times 10 minus 5. So minus 1 to 10 minus 1, 9th power, times 30 minus 5, right? Or the observing order of operations, 30 minus 5. Not 10 minus 5 times 30, no. The multiplication has a higher order of priority than the subtraction. So 3 times 10 is 30, minus 5, 25. So what do we have? Negative 1 to an odd power, it's still negative 1, times 25, we get minus 25. Okay, like that. So are you becoming more comfortable with how to calculate, how to use the nth term of a sequence to calculate the numbers in the sequence? That's what we can do. One of the useful applications of the nth term of a sequence. So A15 would be negative 1 to 15 minus 1 power times 3 times 15 minus 5, right? So that'll be negative 1 to 14th power times 3 times 15 is 45. 45 minus 5 is 40. Minus 1 to an even power, this minus goes away. So we end up with positive 1 times 40, or 40. Okay? Like that. Okay, I hope these answers matched what you have. Next, it says finding the general term, the equation for the nth term. So what we did so far, we used the nth term, right? We used it. But there is a way we can find these too, right? How do we find these nth term sequences? Okay. So basically, this is the idea. To find the general term of a sequence, look for the pattern. You know a sequence is a list of numbers with a pattern in them. So look for that pattern and use that pattern to write the equation for the general term. So in these examples, we ought to do that. So look at that. The pattern there is 3, 9, 27. So it would be a good idea if you pause the video and wrote down the nth term, the general term for this sequence. Okay? If you want to do that, okay, so I'm assuming you've done that, and now you're back. So this is each term times 3 times the position where that number appears. So what is the position of 3? N equals 1, right? N being the position of that number is 1. What is the position of 9? N equals 2. What is the position of 27? N equals 3. And so on. Okay? So then it seems there is a connection between 3 and the position of each number as power. Right? So then so there is a connection between 3 and the position of that number as power. So 3 to first power is 3. 3 squared is 9. 3 cubed is 27. Okay? So then we can write AN is equal to 3 to nth power. And n is equal to 1, 2, 3, and so on. So that's the nth term of that sequence. Okay. Next, we have this kind of sequence. And again, we should look for a pattern. Okay? The pattern is, if you look at each number, it is equal to that number plus 5. This number is equal to that number plus 5. That number is equal to 3 plus 5. Plus 8 plus 5, 13. 13 plus 5, 18, and so on. Whenever you have a pattern that shows the same number added or subtracted, it makes no difference. If the pattern is that the same number is added or subtracted to get the other number, the next number, you have what is called an arithmetic sequence. Let me write that down. So whenever the pattern is that any number in the sequence is obtained by adding or subtracting the same number then we have an arithmetic sequence. Okay. So how do we find the nth term of an arithmetic sequence? Well, we have a formula for that. an equals a1 plus d times n minus 1. This is how we find the nth term of an arithmetic sequence. D is the common difference. D is the common difference. In this case, it is. How do we find the common difference? You take any number and subtract the previous number from it. So D in this case, the D in this case is, and it doesn't matter which numbers you subtract. So 8 minus 3 is equal to 5. You can do 3 minus minus 2. You still get 5. It's the same number. See, adding or subtracting the same number, that's an arithmetic sequence. So D is equal to 5. So we can plug in here. We can let n to be free because we're looking for the nth sequence, nth term in the sequence. So what is A1? A1 is the first term. What is it? It's negative 2. We know A1 is negative, we know A1 is negative 2. The common difference D, A1 is the first term. D is the common difference. I've shown how you can obtain it. You can subtract any two numbers. 13 minus 8, 5. 18 minus 13, 5. 3 minus minus 2, 5. I just picked 8 minus 3. Okay, so D is 5, A1 is negative 2. Let's find the nth term of the sequence. So AN would be equal to A1, which is minus 2, plus D, which is 5, times n minus 1. Okay, so let's do the algebra on this. AN is equal to minus 2 plus, distribute this, plus 5n minus 5. Then AN is equal to minus 2 minus 5, that's minus 7 plus 5n. So there's the nth term of that sequence, with n, of course, starting from 1, then 2, and so on. Okay? So plug in for n with 1. You get minus 7 plus 5, which is minus 2. You get the first term. Plug in for n with 2. Minus 7 plus 5 times 2, 10. Minus 7 plus positive 10, it's positive 3. You get 3. Plus, or plug in 3. Minus 7 plus 5 times 3. 15 minus 7 is 8. There you have it, and so on. Okay? But that's an arithmetic sequence. And how did we notice that? Just looking at the pattern. You add 5 to each previous term, you get the next one. It's always the same number. Okay? All right. The next one, the next set of numbers, we have square root of 2, 2, square root of 6, right? So what's happening here? This number is in position 1, right? This number is in position 2. That number is in position 3. 2 square root of 2 is just square root of 8, right? So do you see a pattern? Do you see a pattern between the numbers and the position where they appear? Because there seems to be a radical expression involved, for sure. But sometimes the radical expression drops out and we get a 2, and sometimes it's there. Sometimes it simplifies to another number, 2 square root of 2, which is 8. So this would be square root of 8 without simplifying. So there is a connection between each of these terms in the sequence and where they appear. Let's try this. AN is equal to, how do we get square root of 2? Square root of 2 times square root of 2n should give us what we need. Okay? Then if you place n equals 1, you get square root of 2. If you substitute for n with 2, you get square root of 4, which is 2. If you substitute for n with 3, you get square root of 6. If you substitute for n with 4, we get square root of 8, which is 2 square root of 2 is square root of 8, and so on. If you substitute for n with 5, we get square root of 10. All right? So this is just, like I said at the beginning of this discussion, the pattern that we have in a sequence is not only between the numbers that are listed, but also between those numbers and the position where they appear. In this case, by noticing that there is a connection between these numbers and the position they appear, we could write the nth term for that sequence. Okay. Now, if somebody asks you, what is in this infinite sequence, because of that dot, 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 that's an infinite sequence, what is the number in the 1500th position? Do you have to list 1,499 numbers to find out what's the 1500th number? No. You simply can use n 1500 and find out exactly what that number is using the nth term of that sequence. Okay, that's why the nth term sequence formulas are so important. So it's important for us to also define n, because n not always starts at 1. So by listing it here as n equals 1, 2, 0, and all the way to infinity, I'm making it clear where n starts. But like I say, it doesn't have to start at 1. We can define n to start at any place that makes sense for that particular sequence. For example, in one of these previous examples that we did, remember that first one on the first page? On the first page, for this sequence, n started at 3, and any number greater than 3. So you can define n to start from anywhere that you want it, as long as it makes sense to compute the terms in a sequence. Okay? In this case and the previous one, n should start at 1. And so I defined it as that. Okay, so next, let me give you a hint on this one as you pause the video to come up with the nth term of the sequence for this on your own. This is another arithmetic sequence. Okay? So write this sequence down on a piece of paper, this one, and notice that it is an arithmetic sequence, so this applies to it. This formula for finding the arithmetic sequence, the nth term of an arithmetic sequence, applies here as well. Okay? And use that formula to find the nth term of this sequence. Okay? Use that to find the nth term of this sequence. And please pause the video, do that, and come back. And By that I mean you have to figure out what D is, what A1 is, what D is, and N is N. N can be free, and then you can find the nth term sequence. Okay, I'm assuming you've done that, and now you're back. So once again, notice that if you subtract this time minus 3, if you subtract 3 from this minus 1, you get minus 4. Subtract 3 from minus 4, you get minus 7. Subtract 3 from negative 7, you get negative 10. So this is definitely an arithmetic sequence. So, and D, you can take any two terms and subtract them. So minus 10 minus minus 7, minus 10 plus 7, so minus 3. So D is negative 3, A1 is negative 1, and this is an arithmetic sequence. So before we do this, before we find the D, which is the common difference, we note that this is an arithmetic sequence. Okay? So, which means we can apply this. AN is equal to A1 plus D times N minus 1. That's the formula for it. That's the formula to find the nth term of an arithmetic sequence. So let's apply it here. AN is equal to A1, which is negative 1, plus D, which is minus 3, times N minus 1. Okay, so let's simplify. AN is equal to minus 1 plus, distribute minus 3 into N, minus 3N, distribute minus 3 into minus 1, positive 3. Okay, so simplifying this, minus 1 plus 3 is positive 2, minus 3N. So we've now found the nth term of that sequence. And of course, let me substitute here that N starts at 1, 2, 3, and so on. Okay? So if you plug in for N with 1, what do you get? 2 minus 3, which is minus 1. Right? If you plug in for N with 2, what do you get? You get 2 minus 6, which is minus 4. If you plug in for N with 3, what do you get? 2 minus 9, which is minus 7. If you plug in for N with 4, what do you get? You get 2 minus 12, which is minus 10, and so on. Okay? All right, so after having this discussion about sequences, this was a basic introduction into that. And like I say, if you have to take Calculus 2, you will delve deeper into sequences and series in that course and beyond. And then, so sums and series, these are sums and series refer to that. These refer to some of the terms in a sequence. Okay, that's what sums and series are. We add the terms in a sequence or series. Okay, so given the infinite sequence like that, the sum of these terms is called the infinite series. And it's infinite series because you have infinitely many terms. Okay, and it is written as follows: A1 plus A2 plus A3 plus so on and so forth, right? Which is that. Refers to the sum of the terms in a sequence. All right? A partial sum is the sum of the first n terms, and it is also called a finite series, and it is denoted as Sn. So it's a finite thing. Partial sum is a finite series, finite. It's not infinite, It's finite. Okay. The partial sum can be written as, notice that it ends, right? It has an end because it has a partial sum. It's a chunk of the sequence that you take and for which you add the terms in it. Okay. So here it says find the indicated partial sum for the sequence, for the given sequence. So they want us to find the sum of the first two terms. Okay, sum of the first two terms. That would be S2 is 1 plus -3, -2. That's it, right? The sum of the first two terms. 1 and -3 are the first two terms. Add them up. That's the sum of the first two terms. For S5, or the sum of the first 5 terms, so we have 1 plus -3 plus 5 plus -7. How many terms is that? 1, 2, 3, 4. One more, right? Plus 9. So 1 minus 3 is -2, plus +5, +3, plus -7, -4, plus 9, +5, like that. Okay. Okay, so then the next one, we can do the same thing with the next one, right? Please pause the video and find the partial sum, which is S1 and S5. S1 should not confuse you, right? S1 is simply the first term. So I'm assuming you've already done that, and now you have your answers. So S1 is simply 1. That's it. One term, the sum of the first term, 1. Right? Now S5 means 1, 2, 3, 4. All these 5 terms, we need to add them. So 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25. You should not convert these numbers to decimal and add them like that. No, because, I mean, you could do that if all of these were some number that you didn't have to round them. But see, if they're not like that, not all of them are like that. So if all of them were like 1/4, see, 0.25. So if all of these ratios would reduce to some number like that had an end, then you could convert all these to decimal values and add them up. But look what happens for 1 over 9. 1 over 9, look at that, right? That's not exact. That's just a rational number, 0.11111 forever, right? So you'd have to round, in which case your answer would not be exact if you use the decimal value. So you must keep everything in fraction form. Okay? That means, in this case, we need to find the common denominator. I remember when I taught Math 95 a very long time ago, we showed everybody how to take the common denominator by finding the prime factors of all these denominators. So the prime factors of 4 are 2 times 2. Prime factors of 9 are 3 times 3. Prime factors of 16 are 2 times 2 times 2 times 2, and prime factors of 25 are 5 times 5. And then the common denominator, or LCD, least common denominator, would be any of these factors, any of these numbers, in the largest number of times it would appear under any given number. So 2 is present, but it's present here in 4 times as a product of itself 4 times. So we need to include in the LCD, we shouldn't include 2 times 2, but 2 times 2 times 2 times 2 4 times. So 2 times 2 times 2 times 2 times 2. And then the 3 twice it appears, times 3 times 3. And of course 5 appears twice, like that, under one number. So this is our LCD. We can calculate that. So this will be 25. 5 times 5 is 25 times 9 times 16, right? So 3,600. So 3,600 is the LCD for this, the common denominator for these fractions. Okay, so then if that's the LCD, then we have 3,600. So 3,600, we know the denominator for this first term is 1, right? So compare that with the common denominator. What's missing from it is 3,600. So we must multiply 1 by 1,600. So 1 times 3,600. Plus, compare this with this common denominator. What's missing from this common denominator 4? Let's find out. 3,600 divided by 4, 900, right? So 900 times 1, we multiply the numerator by what's missing, by the factor that is missing from the denominator, right? So 900. What's missing from this denominator when you compare it to the common denominator? 400, right? So multiply the numerator by the missing factor. What's missing from comparing the 16 with 3,600? What's the missing factor? Well, let's find out. 3,600 divided by 16. 225. So we're going to multiply 1, the numerator of that fraction, by 225. Okay. Plus, compare this with 25. What factor is missing from the 25 to give us 3,600? Let's find out. 3,600 divided by 25, 144. So we multiply the numerator of that fraction, which is 1, by 144. Okay. All right, so I'm running out of room here. Let me move up here, in here. Okay. So now we're going to add all of these. 3,600 plus 19,900, that's 4,500. 4,500 plus 400, that's 4,900. 4,900 plus 225. 4,900 plus 225, 5,125, and that plus 144, we get 5,269 divided by 3,600. So we have 5,269 divided by 3,600. And I do not mind at all can we simplify this? Let's see. I don't know. 5,000. Let's try some numbers to see if we can simplify that. 5,269 divided by 3, it didn't work. but let's say by 5, no, it doesn't work. It doesn't look like it. No. So, but I don't mind to double check my numbers here once again, just to be sure that my numbers are correct here. 3600 plus 900 plus 400 plus 225 plus 144. Yep, 5,269. So that's that. So that's the sum of the first 5 digits in this sequence, or S5. Okay. All right, so sigma notation, this is just a description of a notation you'll see a lot when you deal with sums and series of sequences. You'll see this notation a lot, this one. Okay, it's the Greek letter known as sigma. Notice in the Greek alphabet we have lowercase and capital case letters, right? So this sigma, this is the capital sigma. The lowercase sigma, so this is capital, this is sigma, but it's this is the capital letter, sigma. What about the lowercase? The lowercase sigma is that. So this is also sigma, and this is lowercase, or capital case, or capitalized. So this is the capitalized, I should say capitalized, not capital. Capitalized, and this is the lowercase letter. I say this because if you take statistics, a lot of times you see this letter, and it's called sigma. And I don't want you to get confused if you see this letter called sigma. It's just this is the capitalized version, this is the lowercase version, but they're both sigma in the Greek letter alphabet. Okay, so can be used to denote a sum when the general term of a sequence is a formula. So that's the notation whenever we write the general sum of a sequence using a formula like that. So this is read the sum. This is how we read this notation. This is read the sum as k goes from 1 to 4. Okay? Goes from 1 to 4 of this expression, 2k plus 1. And this k is called the index. Sometimes the letter I is used, in which case that would be 2i plus 1. But if you use k, the index as k, you say 2k plus 1. But it's the number from which it starts at that number and it ends at that number. So k is being incremented at 1, starting at 1, ending at 4. Okay? So there it is. The letter k is called the index of summation. Right? This is very important. The index of summation. The index of summation might start at a number other than 1, and letters other than k can be used. Okay? So let's evaluate these sums. Okay? So here, they're saying evaluate this sum, and the index is not k, it's I. It's just another letter, which is fine. We don't have to use k or I. We can use any letter. We can use n if we want. So it says evaluate this sum such that I, or the index, starts from 1 and ends at 6. And these numbers always increment as whole numbers. So the next number is not going to be 1.2. It's going to be 2, 3, 4, 5, 6, and so on. Okay? So let's calculate this sum. We have 1 over 2 times 1. It starts at 1, ends at 6. Plus 1, plus 1, 2 times 2, plus 1, plus 1 over 2 times 3 plus 1 plus 1 over 2 times 4 plus 1 plus, right? We have to go all the way to 6. 1 over 2 times 5 plus 1 plus, last one, 1 over 2 times 6 plus 1. Okay, are you following this? I hope you're following what's going on. It's pretty straightforward. Just increment I from 1 to 6 and add each one. Each time you change increment, add it to the next one. Okay, so what do we have? We have 1 over 3 plus 1 over 5 plus 1 over 7 plus 1 over 11, right? 2 times 5 is 10 plus 1 is 11 plus 1 over 13. 2 times 6 plus 1. Okay, so once again, here we have to find the LCD. So all of these are prime numbers. So the LCD is simply 3 times 5 times 7 times 11 times 13, right? So the LCD is, let's find that out from my calculator here. It is 15 times 7 times 11 times 13. 15,015. Okay, and then then we have 15,015 as the common denominator. So compare this common denominator with this 3. What factor is missing? Let's find out. Oops, sorry. I think that's not correct. I didn't write the whole number. Sorry about that. I just didn't see it. Let me double check that. 15 times 7 times 11 times 13. 15,015. So there is a 1 missing here. 1. Okay, that's correct now. 15,015. So this should be 15,015. Like that. Okay, so comparing this with the 3, the missing factor is 5,005. Right? So let's multiply the numerator, which is 1, by the missing factor, which is 5,005. Plus, compare 5 with 15,015. What's the missing factor? Let's find out. We have 15,015 divided by 5, 3,003. So the numerator of that fraction, which is 1, should be multiplied by 3,003. Like that. Plus, compare 7 with 15,015. What's missing from it? Let's find out. 2,145. So we multiply the numerator of that fraction by the missing factor. 1 times 2,145. Okay, compare this number with 11. What is the missing factor from this denominator? Well, let's find out. 15,015 divided by 11. What do we get? We get 1,365. So multiply the numerator of that fraction by 1,365 plus. What is the missing factor from 13? let's find out. Divided by 13, right? Oops, I forgot to press the division button. Divided by 13. 1,155. So multiply that numerator, which is 1, by 1,155. Okay, so let's add. All of these are being added by multiplied by 1, so we can add those numbers together. Let's do that. So I don't know if I can fit all of that on the screen. Let me try. I think I can, like that. Yes. So that way I can show everything on the screen. So let's add all the red ink numbers. So 5,005 plus 3,003 plus 2,145 plus 1,365 plus 1,155. 12,673 divided, of course, by 15,015. So the final sum is 12,673 divided by 15,015. So we want to leave our answers in this fraction form. I mean, if you divide by 15,015, you get something like that, which then you have to round, which is not exact answer. Okay, so it's better to leave the sums or series in fractional format. Okay, so you might want to pause the video and answer these 3 questions. All they're saying is saying find the sum of these 3 problems. So this one you have to start from k from 4 and go up to 7. Start k from 1, go up to 4. This one, k starts at 0, so you got to be careful about where the index of the sum starts at. Okay, all right, so let's plug in. So all we have to do is increment the k from 4 to 7 and add the results. So we have square root of 2 times 4 minus 1 plus square root of 2 times 5 minus 1 plus square root of 2 times 6 minus 1 plus square root of 2 times 7 minus 1. Okay, so 2 times 4 is 8 minus 1 square root of 7 plus that's square root of 9 minus 1, 10 minus 1, 9, square root of 9, and plus square root of, that's 12 minus 1, that's square root of 11, and plus that's 14 minus 1, so a square root of 13. Okay, so the sum here, the only one that can leave the square root is 9, so that'll be 3, and then so we have square root of 7 plus 3 plus a square root of 11 plus square root of 13. I think these are maybe even square root of 11 or square root of 7. These are irrational numbers, so square root of 7. Oops. So square root of 7. So like that, right? I mean, I would leave it like this. I would personally leave the answer like that unless I'm asked specifically, I'm directed to give an approximate and decimal value answer. So if I'm not asked to do that, I will leave my answer like that because that's exact. But of course, if they ask you to convert the answer to something in decimal form, then you can approximate it using your calculator. Okay. All right, so this one, it is, so k increments at 1 up to 4, and that's, so pi times 1 plus pi times 2 plus pi times 3 plus pi times 4. So what do we have? We have pi plus 2 pi plus 3 pi plus 4 pi. So we have pi, 3 pi, 6 pi, and 10 pi, right? 10 pi. And that's the final sum. Okay. All right. So next one. This is saying increment the k with from 0 all the way to 7 and add the results. So let's do that. So we have minus 1 to 0 power, right? K starts at 0, goes up to 7, times 4 to 0 plus 1 power, plus minus 1 to power 1 times 4 to 1 plus 1 power, and plus minus 1 to second power times 4 to 2 plus 1 power, plus minus 1 cubed times 4 to 3 plus 1 power, and so plus minus 1 to fourth power times 4 to 4 plus 1 power, plus minus 1 to fifth power times 4 to 5 plus 1 power, plus minus 1 to sixth power times 4 to 6 plus 1 power, plus, of course, minus 1 to seventh power times 4 to 7 plus 1 power. Okay, oops, I'm off the screen there. All right, so now we have to simplify this, of course. Let's do that here. So anything to 0 power is 1. 1 times 4 to first power, 4 times 4 to first power is 4 times 1 is just 4. Okay, plus. Minus 1 to first power is minus 1 times 4 squared. That's 1 plus 1. 4 squared is 16 times that. 4 plus minus 16. Plus. Minus 1 squared is just 1. 4 cubed is 64. Right? 64. 4 cubed is 64. 64 times positive 1 is 64. Right? Plus. Minus 1 cubed is minus 1, or minus 4 to fourth power. Right? Let's see what that is. 4 to fourth power. 4 to fourth power is 256. So minus 256. Plus, we're done with that. Let's come to this line. So minus 1 to the fourth power is positive 1 times 4 to fifth power. What is 4 to fifth power? Let's calculate that. 4 to fifth power, 1024. So 1024 plus minus 1 to fifth power, that's minus 1, so it's preserved because 5 is odd power, and then times minus 1 times 4 to sixth power. What is 4 to sixth power? 4096 plus minus 1 to sixth power, that becomes positive 1 times 4 to 7th power. Let's see what that is. 4 to 7th power is 16,384 plus minus 1 to 7th power. 7 is odd power, so minus 1, minus is preserved. That's plus minus 4 to 8th power. Let's see what 4 to 8th power is. So 4 to 8th power, we have 65,536. Like that. Okay, so now we need to add all these terms. Okay. So we have 4 minus 16. Let me make sure that all of this is visible like that. Okay, that's better. 4 minus 16 plus 64 minus 256 plus 1,224 minus 4,096 plus 16,384 minus 65,536. What do we get? We get minus 52,428. Minus 52,428. So there's the sum. Okay, like that. All right. So now let's in the next exercise, it says write these sums. These are sums, right? If there were sequences, we would see a comma in between them. But they're not sequences, they're sums. So it says write sigma notation for each of the sums below. Okay, let's do that. So what is this saying? This is saying 7 plus 7, again 14 plus 7, again plus 7. Okay, so this would be, and this is an infinite sum. So we have sigma and 7n, right? 7n is the sequence. N is 1. When n is 1, the sequence would be 7. When n is 2, 14. N is 3, 21. 4, 28. 5, 35. So that's so an, so for this, an is equal to 7n. That's the nth term of this sequence. But they want us to write the sum. So the sum would be the same thing, 7n, but this is an infinite sum. So the n, because I used n, so I should use n. If I used I, this would be I. If k, this would be k. So I used n, so this should be n equals to 1 to infinity, because this is an infinite sum. So that's that. But before you do this, you need to figure out what the nth term sequence is. First, so let me write this down. First, figure out the pattern, right? First you have to figure out the nth term of the sequence, which is that. After you figure this out, you put that in the sum, and then you index it. Okay, you index it from 1 to infinity, because this is an infinite sum. This is not an infinite sum. Next one, right? So you might want to pause the video and do that and answer all of these. answer all three. So please pause the video, figure out the sum notation for all these sums, and then come back to the video. All three should not take you more than 10 minutes or something like that. Okay? These are not hard problems at all. Okay, so I'm assuming you've done that and now you're back. So we need to first figure out the nth term of the sequence. And that not only goes for this, it goes for that, it goes for that, and it goes for that. For all the other problems, we should do that. We should first figure out the nth term of the sequence. Okay? Now, for this one, notice that this is the first term in the series, right? And you have 1. The second term, you have 2. Third term, you have 3. Fourth term, you have 4. Fifth term, you have 5. So there's definitely a connection between each term in this series and the position of that number in the original sequence. So the nth term of this sequence must be 1 over n squared. That's the nth term of this series, of the sequence that is behind this series. So all we have to do then, once you figure this out, then the sum, it's going to be easy to write down. So you say sigma, I used n again, so I'm going to use n. This time, this is a finite series or sum. So 1, 2, 3, 4, 5. So n goes from 1 to 5 of 1 over n squared. Like that. Okay? So that is the sum of the terms in this series shown using the sigma notation. Using the sigma notation. Okay? The third one, notice there's a pattern, right? The way it's been written is very nice, and it can tell us that there is a pattern right there. This also suggests, suppose they had given us 1 over 4, 1 over 18, 1 over 48, so we would, this is also implying that if we were given the whole numbers here, we should write the whole numbers in the denominator in a product of terms that shows a pattern, that unmasks the pattern. Here they've done it for us in this example, but it also means that if it was not done, we should do that. We should look for this pattern, right? But the pattern is pretty much uncovered for us. So they've made life easy for us. Well, let's see what the nth term is. The nth term is, again, this term in connection with its position, which is the first position. See, first position, second position, third position, fourth position. And then the number that has been raised to squared or squared is always 1 plus the position number. So 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. Okay, so the nth term of this sequence must be n times n plus 1 squared. Okay, that's the nth term of that sequence. That's why we said first figure out the nth term of the sequence for all of these. Then worry about the sum. So then we can write the sum is, this is again an infinite sum, so n goes from 1 to infinity, and this whole thing ends up here, 1 over n times n plus 1 squared. Like that. Okay? And that's just an arrow. That's just an arrow right here. Okay. All right. So this next one, I hope this matches what you had on your paper. This next one, it's again, they made it easy because we have the nth term sequence right there. That is the nth term sequence. Okay? But we got to be careful because we have to be careful about from where n starts indexing or starts incrementing. So from wherever it starts, we should get 9 for the first term. Do we get 9 if we put n equals 1? No, we're not going to get 9. Do we get 9 if n increments at 2? No, we're going to get -4, not positive 9. Do we get not positive 9 if we increment n at 3? Let's see. 3 plus 1 is 4. The n minus 1 drops out, and 3 squared is positive 9. Do we get -16 if n is 4? So let's see. N minus 1 to 5th power is -1. 4 squared is 16. So -16, correct. So yes. So we have to be careful here. Then the sigma notation of this would be n equals 3, not 1, not 2, not 3. N starts at 3 and goes all the way to whatever that n it's gonna be. So let me first complete this. -1 to n plus 1 times n squared. So this is a finite value. So I don't want to put infinity. N goes from 3 to, let's see, from 3 to wherever n stops. So let's see. So because n is left free, then n goes from 3 to wherever the n stops. So I'm going to put n again, but not infinity. This is not an infinite sum. So n goes from 3 to wherever n stops. If n stops at 10, then that's 10. From 10 to 10. From 3 to 10. Okay, to wherever n stops. So 3 starts at 3, but ends at wherever that n stops. So I'm just going to leave it like that. Okay, but definitely not infinity. Okay. All right, so the next one, recursive sequences. These are really, really interesting sequences because recursive sequences are sequences that look back at the previous term. So if you want to know what is the second term, you must know what is the first term already. That means you must be given the previous term. Otherwise, you cannot calculate the nth term. So this is why recursive sequences, you always want to calculate these with a computer. Because if you're given the first term, and then all of a sudden in the recursive sequence, you want to know what is the 520th term, then you need to know what is the 519th term. But in order to know what is the 519th term, you need to know what is the 518th term. So if you're doing this manually, you're going to have to list 519 terms before you know what is the 520th term. Manually, this will become very, very laborious. So recursive sequences yield themselves very well to use of computers or computer programming. Okay? But here are a few examples. a few simple examples that we could do manually without spending too much time figuring out the terms. Okay? So that's what I just said is basically, please read these sentences because what I just said is captured right here. Recursive sequences is sequences finding each subsequent term in the sequence depends on knowing and finding the previous term first. That's why I said if you want to know the 520th term, you need to know what is the 519th term, and so on and so forth, right? So they're different than the arithmetic sequences or the sequences we've looked at so far. Okay. So this one, given this recursive sequence, see, they've already given us the first term. A1 is equal to 256, and they want to know, find the first 4 terms. So we need to calculate only 3 terms. But because this is recursive sequence, they had to give us the first term. Otherwise, we couldn't calculate the subsequent terms. So since we already know the first term, then let's calculate the second term, which would be A2, right? A2 would be so A1 plus 1 would be A2, which is equal to square root of A1, right? For N1, that would be A1. So A2 is square root of A1, which means square root of 256. Okay, let's figure out what is the square root of 256. 16. Okay, like that. So then, this was A2. Okay, but in order to calculate A2, you have to calculate A1 plus 1. So this is A2, and this is A1, okay? So to get to A3, we must have this n as A2. So A2 plus 1 is equal to A3, which means it's equal to square root of A2, okay? So we already know A2, so square root of 16 is equal to 4. And this is A3. And A1 is already there. A4, right? A4 would mean 3 plus 1, right? 3 plus 1 would be A4. That means square root of AN would be square root of A3 equals square root of 4, which is 2. So this is A4, or the 4th term in that recursive sequence. Okay? So this next one is, so I'm strongly encouraging you to please pause the video. You have 2 problems here. Answer these and then come back to the video. Okay? It should take you 10 minutes, and that will go a long way in helping you understand this topic if you give yourself the opportunity to first generate your own solution. So please don't skip that step. All right, so I'm assuming you've done that. You have your own solutions, and now you're back. So here, we already have A1, so we need to calculate 3 more terms in this recursive sequence. So A2 would be A1 plus 1, right? So that would be A2, and this is saying take the natural log of A1, which is natural log of e to q power. Okay, that's A1. Natural log of A1 is the natural log of e to q. Okay, we know from the properties of natural logarithms that this q, the exponent, can come down and in front and multiply itself by natural log of e. again, we know from the properties that we learned about that natural log of E is 1. So q times 1 is q. So this is A2. A1 is here. A2 is q. Okay? Then, to find A3, this n has to be 2. So A2 plus 1 is equal to A3, which means this is equal to natural log of AN. AN in this case, it was A2. So A2, so we need to take the natural log of that. Natural log of Q, and that's that. That is A3. Okay. Finally, for A4, to calculate A4, AN has to be 3, A3. So A3 plus 1 is equal to A4, which means natural log of A3. A3 is that, so this is equal to natural log of Q. Okay? So this is equal to A4. Okay. So now we have the next problem here. Okay. So I'm assuming that you've already also finished this. A1. So in this case, this is a different recursive. In this case, they had to give us, because of the way the recursive sequence is given, they had to give us two terms, two of the previous terms, and they're asking us for A3 and A4. So we already have two of these answered for us, which is fine. We need these. That's the nature of recursive sequences. So we need to find two more terms. So to find A3, this AN has to be 2. 2 plus 1 is equal to it's equal to A2, right? I'm just making sure that I plug in what numbers we should have. A2 minus A2 minus 1. So let's simplify this. This would be A3 is equal to A2 minus A2 minus 1, A1. Okay? So, therefore, I'm trying to save space here a little bit. If you don't mind, I'm going to put the rest of the solution right underneath this, because I'm going to need this for finding A4. So let me try this. A3 then is equal to A2, which is 8, minus A1, which is minus 10. So therefore, I need to come up here. Therefore then, A3 is equal to 8 plus 10, or 18. Okay, that's A3. Now A4, for finding A4, this AN has to be 3. So A3 plus 1 equals A3 minus A3 minus 1. Let's simplify that. So A4 is equal to A3 minus A3 minus 1, A2. Do you see how recursive sequences work? The whole purpose of this exercise is to give you an idea about how recursive sequences work. Look how each term is tied to either one or multiple previous terms. In this case, every subsequent term is tied to previous two terms. as you can see here and here. A3 depended on A2 and A1. A4 depends on A3 and A2. Okay, so let's plug in then. A4 is equal to A3, which we've solved for 18, minus A2, which we were given as positive 8. So therefore, A4 is equal to 10. Okay, like that. Okay, like that. So here we have, basically you have everything on the screen for this one, and for this one, for this problem. Okay. All right, I hope this discussion helped simplify or clarify the subject of sequences and series. With these problems, you have to review this stuff, so please make sure that you revisit these problems again in the video and in the book section without looking at the solutions. Answer them again, and that way you feel you build confidence and you build knowledge about this content. So thank you again for persisting through this video and watching it all the way to the end. For now, have a very nice day, and I'll see you all again next time.